Hello, everybody. Thank you so much for joining us today. My name is Jen McConnell, and I am the product manager here at Protochips. And we thank you so much for being here. This is our first webinar in our newest series called Amp Up Your Devices, Studying Electronic Devices within Situ TEM. The series is going to focus on research published using in Situ TEM, specifically our Fusion AX system, to study different nanoelectronic devices. Fusion AX can be used to study different semiconductor devices such as FinFETs, ReRAM devices, solid state storage devices, etc. And so hopefully this series will inspire you as to what is possible with the system and what you can do with your research. As the introductory webinar to this series, today we're going to focus on giving you an overview of the Fusion AX system, and also discussing the importance of different design aspects to achieving quantitative nanoscale electrical measurements. And today will be presented by our product specialist, Dr. Zayna King, and our Chief Technology Officer, Dr. Damiano. Before we get started, I have a couple small housekeeping items. Everybody is going to be muted due to the audience size and to prevent accidental interruptions to the speakers. So if you have questions, please enter them into the questions box that should be on your GoToWebinar panel. And we're going to handle all the questions for both speakers at the end of both presentations. So all of them will be done at once at the end once both are done speaking. And we are recording this, so if you cannot stay, that's okay. We'll be sure to share this afterwards. There'll be an email that goes out with the recording link for you to watch the rest of it. So without further ado, let's go ahead and get started. Our first speaker is Dr. Zayna King, and Zayna is the product specialist here at Protochips, and she's going to start with the overview of the Fusion AX system. Zayna, the floor is all yours.
Thank you, Jen. Does everything look good? My screen, you can see everything.
Yes, ma'am, it all looks good. You sound good. You're good to go.
Okay, good. Hi, everyone. I'm Zayna, like Jen mentioned. I am opening up this series. It's really a great series that we're starting off. And I will introduce the Fusion AX system. But in general, this entire series will focus on using this heating and biasing system, in situ TEM system, for characterization of electronic devices. So let's get into it. For those of you who are not as familiar with Protochips and who we are as a company, we are a US company and we're based in North Carolina on the East Coast. We have about 50 employees that are scattered throughout the globe that serve service, application support, sales support, and so much more. We started this company was created in 2002, very long ago, and we developed the first MEMS-based heating holder, which was a version of this holder that I'm about to present today. Other than after the inauguration of this MEMS-based holder, we've developed several other in situ TEM holders to further support in situ TEM experiments in other realistic or relevant environments in the TEM. So again, for people who are not as familiar with and not as familiar with transmission electron microscopy, basically it's an imaging technique that involves transmitting a beam of electrons through a sample to create an image. This provides a lot of valuable information about the structural and chemical composition of your sample down to the atomic scale, which is very, very important for material science research. However, one caveat of the electron beam is that it requires a high vacuum environment, which then limits the type of samples that you can study in the TEM. And so along with limiting sample type due to the vacuum environment, traditional TEM is also limited to studying materials in a static state, which consequently means that we cannot capture any sort of dynamic information about the sample. Many of the materials that we want to study in the TEM also do not operate in a vacuum environment, and so to take advantage of the high resolving power of the electron microscope, we had it was important to create a sample holder where you can study these dynamics in a very realistic environment for these materials that were unable to be assessed in the TEM. And so many of the materials that we wanted to study, like I said, from energy production, energy storage, corrosion research, a lot of these materials, the vacuum environment is not appropriate for studying them, and so hence the idea of in situ TEM. And most of the researchers that we know tend to incorporate in situ TEM into their research, because while benchtop experiments can reveal a lot of information about, a lot of functional information about materials, understanding how the nanoscale components simultaneously contribute to the overall function of the material that you're studying is extremely important. And this nanoscale information is especially important for driving material improvements or developing more efficient processes or better materials, more robust materials in the future. And while this is not an exhaustive list of all of the different applications of in situ TEM, here are some of the major application areas where we find a lot of customers doing research. With such a wide range of application areas, it's clear that in situ TEM is a well-accepted technique in the science community, and it can provide critical information about material behavior. So to support the wide, that range of applications that I just showed, Protochips has developed a suite of in situ TEM systems for various applications. So in the TEM lab, you have the in situ TEM system. So Fusion AX, which is our focus today, our heating and biasing holder. We have two liquid cell holders, Poseidon AX and Triton AX. And then we have a gas for pressurized gaseous environments, the Atmosphere AX. And these are all run on this software platform called Axon Synchronicity, which communicates with both the in situ systems as well as the TEM and aggregates, pulls all of the data from these multiple pieces of your in situ TEM system to aggregate them so that you have them once you're done with your experiment. And speaking of which, we also have an offline platform of this software called Axon Studio that's free to download on Apple Store or the Microsoft Store, where you're able to pull in all of the data that you've acquired on synchronicity, including all of the metadata, all of the image data, into a free software that you can analyze your data really quickly. And what's really useful about this also is the fact that all of your collaborators are welcome to download the software, so then you can share data, usually large subsets of data, typically. Now you can share them through Axon Studio, where your collaborators are also able to receive the metadata as well. Okay, with that said, I will introduce our Fusion AX system, again, which is the focus of our series for the next couple weeks. So Fusion is our heating and biasing holder, as I mentioned, and it is our solution for electronic devices research. It's our most mature system. It was brought on the market, about over 15 years ago, and several of the unique features about this system set it apart from other heating or biasing holders on the market. It's very widely adopted. There are plenty of systems around the world. We also provide support, like I mentioned, around the world. And in addition to electronic devices, the Fusion AX system can also support research on ceramics, semiconductors, electrical devices, and more. So now that I've introduced fusion, I want to just briefly go over electronic devices. I'm sure many of you here are very familiar, but for those who aren't, electronic devices are a subset of hardware that manipulate the flow of electrical energy to create some sort of signal, transfer the signal, amplify the signal, and more. Circuits, as we know, are the building blocks of these electronic devices. So these little tiny chips that fit into our phones or computers or really any sort of device that we use today. These are the major units of an electronic device. And again, there are plenty of words that might ring a bell, like capacitor, transistor, and resistors, which are all components of these electronic devices. So for electronic devices, a lot of the research focuses on scaling down the size of these devices, also improving the reliability of the devices, lowering manufacturing costs, and ensuring that you get very high yield. Also lowering consumer cost as well, and then understanding any site-specific failures that can lead to premature defects or failure of the system. So to successfully address any of these concerns, investigating the material properties and the device structure and its impact on the electrical performance is very important. And these studies can then inform the development of more scalable or robust devices used in these common gadgets and appliances and more. And the structure, as we know, the structure of materials has a very big impact on how well they perform and how durable they are. And with the TEM, you can gain a lot of information specifically about electronic materials, such as interfaces, junction information, crystallinity, elemental composition. But sometimes that is not enough to really fully understand material performance. To better determine performance across various applications, you have to couple this TEM structural data with tools that tend to measure the functionality of these materials. And in this case, it would be a source measure unit. And with an instrument like that, you can gain insights into the physical properties of the materials, as well as the influence of these physical properties on things like scalability, failure, lifetime, and power consumption. And again, coupling these two complementary pieces of data, so structural information plus the functional information, can then give us a more comprehensive picture of material performance or device performance that can then be used to develop better or more robust devices in the future. And so to be able to address all of these features, it's really important to understand that just having a sample holder, so us providing a Fusion AX sample holder to you is not enough for successful experiments, right? It's really important to have to be supported through an entire workflow, so that you know that from the point of sample preparation all the way through to publishing or sharing your results with others, that you are successful, right? You want to be able to do reproducible experiments regardless of your expert level, so novice all the way up to TEM expert. We want you to be successful doing these experiments. And so across all of our in situ TEM systems, Protochips provides a suite of tools that can speak to each area of the experimental workflow that can help support our customers. And so I'll walk through quickly each of these steps as it applies to electronic device research. So one of the major drivers of a successful experiment is proper sample preparation and sample support selection. For sample support, Protochips uses these MEMS devices, which are called e-chips, that allow stimuli to be added to your sample. So with traditional TEM, you're looking at a static sample. Here, you're able to look at your sample while it's like undergoing a bias or being heated, etc. And these MEM sample supports, which you can see here, they replace the 3mm copper grids that you're used to with traditional TEM. To support the wider range of experimental needs that including electronic devices research, there are many different configurations of these sample supports that depend on the type of experiments that you want to run, as well as the size and shape of the samples that you're using. And so you can perform electrical only experiments, thermal or heating only experiments, and then you also have an option to perform heating and simultaneous heating and biasing experiments as well. For the purpose of this presentation though, and because many of the following webinars in this series are focused on electrical characterization, I will only focus on these electrical e-chips. In addition to selecting the sample support, the appropriate sample support, Protochips also offers a focused ion beam stub for fib lamella preparation and precise loading of your sample, the fib lamella, sorry, onto the e-chip. Fib lamella are often used in electronic devices research to study things like interconnects in a circuit and other things. John Damiano, our CTO, who will follow up in this webinar, he's up next, so please stay tuned, will expand on some of the work where people have used fib lamella to study circuits. While this is not as relevant to electronic devices research, Protochips also offers a shadow mask, which helps for clean and precise sample deposition in the area that you're interested in. And here you can just see gold deposited accurately across the sample area. The viewing area, sorry, of the e-chips, and these specifically are electrothermal e-chips. So as I mentioned previously, the Fusion AX offers a wide range of e-chips, and that gives customers the flexibility to perform any sort of experiment that they want, including heating, biasing, electrothermal characterization, and more. And also, it supports different types of samples. So once your e-chips have been selected and you've loaded deposited your sample on your e-chip, you're now appropriately prepped to insert the sample holder into the TEM. And so at that point, you can begin your biasing experiments, your heating experiments, and more. And with regards to electronic devices, you'll be able to observe things like device structural changes in the device, like interface dynamics, electromigration at interconnects, any sort of thermal or mechanical breakdown over time, changes in crystallinity or elemental composition. And again, you're applying a bias, so you're seeing it under relevant operating conditions. because the focus of this series is electrical characterization, I want to briefly highlight some features that were carefully incorporated into the Fusion AX system to ensure that you're performing rigorous and reproducible electrical experiments. And this is something that John will expand on in his half of this talk, but I just wanted to introduce some quick things here. So firstly, the components and the design of the sample support are, it's really important that this ensures low electrical leakage and parasitics, because any sort of leakage can compromise the validity of your electrical signals and results, right? And so this is just a simple example here where a single titanium wire was used, and they were able to perform experiments at the nanoscale down to like a sub-nano amp and millivolt basis, which again, with such low current and voltage, you really want to have a system that is designed to be very accurate and very precise in its measurements, but also support to prevent noise as much as possible. In addition, Fusion has a wide range. It offers the widest range of friction-free alpha and beta tilt ranges. And beta tilt is usually very important to get to zone axis. And the electrical probes which sit here, they all tilt with the chip when you're performing these experiments. And that's really important because it minimizes any sort of electrical or mechanical noise that can occur during the tilt process. And so you're able to still get accurate electrical, or in the case of a heating experiment, accurate information on your material changes, knowing that you have eliminated any noise due to just the tilting. Oops. And then for electrothermal experiments, which is really not the focus of this series, Fusion is also uniquely designed to perform high resolution electrothermal characterization. And that is because our electrical leads are placed directly on top of the heating membrane. And what that does is it ensures that you create an accurate association between the temperature and the temperature that the sample is experiencing, as well as the electrical characterization of that material. And that's, again, very, very important for people doing electrothermal studies. And lastly, the low profile design of the Fusion AX holder the low profile of the Fusion AX holder, I'm sorry, allows for maximum line of sight to your EDS detectors, which ensures that you get high resolution EDS data in little time while you're studying your sample or applying some sort of stimuli to your sample. As I mentioned previously, Protochips also, all of these in situ systems, including the Fusion AX system that I talked about today, interface with the Axon synchronicity software, which is just machine vision software that communicates with your TEM and your in situ systems, and it provides a level of automation and experimental control in your in situ TEM experiments to ensure that you as the user can focus more on your sample and what's happening on your screen than fiddling with the controls of the TEM. it also ensures that you are because it's connected and communicating with the TEM as well as the holder. It's pulling all of the metadata from these components and integrating them into your data set, which is really important because now you don't have to spend time writing every single change that you make during your experiments. And again, you can focus just on your sample on the screen. And oops, in addition to the metadata integration, Axon Synchronicity also performs image stabilization. So again, you don't have to worry about fiddling with the controls to stabilize your sample and keep it in one position. With heating experiments, biasing experiments, thermal expansion, and more, you typically get some sort of movement of your sample, and so you don't want to focus on correcting that movement. And so Axon Synchronicity provides 4-level drift control to stabilize your sample, again, so that you as the user don't have to focus on that. And then I mentioned once you're done with your experiments, now you can take it to the offline software Axon Studio that supports analyzing or reviewing your data sets in this free software. And so again, Axon Studio will, when Axon Synchronicity collects all of the metadata, so you can see here, you get current and voltage data, you get image data, and so many more pieces of metadata. It's all integrated in your data set that you've acquired from Axon Synchronicity. You bring that into Studio, you still have access to it. Any of the collaborators that you send your experiments to, your results to, will also have access to it, and it's very easy for you to review your data set than having to piece through and use other third-party software just to align your data and more. Protochips, we understand that in situ TEM experiments, TEM in general is not the easiest of techniques. It's not for the faint of heart. And so we want to make sure that regardless of what system that you're using, you are fully supported across the experimental workflow with this online platform where all of our users can access to get information like instructional guides, how to clean the e-chips, how to set up your system, what's in the box, and so much more, where you can really get intimate and learn about your system. We also provide full-time support, but with this online platform, you have 24/7 access to it. And there are even articles that we recommend reading in that software. So I highly, if you have a prototype system, I highly suggest that you take a look at our Success Community platform because it has been incredibly useful to many of the customers that I've spoken to thus far. And just as a quick summary, whoops. Just as a quick summary, I mentioned that there are other products in our portfolio. So there's in situ liquid for liquid heating and electrochemistry experiments, the Poseidon AX. We also have Trident AX for liquid heating and cooling, simultaneous liquid heating and cooling with electrochemistry, and then Atmosphere AX for your gas solid reactions. If you want to learn anything else about these other systems that I didn't talk about today, you can take a look at our website using this QR code, and you're welcome to follow us for all of our updates on any new improvements of the systems or any new systems that we've put on the market on LinkedIn using this QR code. And lastly, I'll give my shameless plug. First, I'll say thank you. Thank you for listening. Everyone, thanks for being here. Thanks for joining this first session. but also there are, I know that I have not done this, this webinar series justice, but there are plenty of other experts who will be speaking about their research, electrical characterization of the different devices that they've been using, in addition to John. So I really encourage you to sign up for the webinar. There should be a link in the chat that you can to access registration for this webinar series. Thank you.
Great. Thank you so much, Zayna, for the introduction. And she's right, there is a link in the chat to sign up for the rest of the series. It's free. You can go ahead and get your name on the registrations for them so that you get the reminder emails when, when they're coming up. And then you won't forget. You won't miss a beat, which is what it's supposed to say in the chat. Nothing about bears. Ignore the bears. I don't know what happened there. So let me introduce our next speaker. We've got Dr. John Damiano. He is our Chief Technology Officer here. He's also a co-founder of Protochips, and he's going to be talking about some of the different design aspects in particular that are really important to achieving quantitative nanoscale electrical measurements. John, thank you so much for joining us today. The floor is all yours.
Thank you, Jen. Thank you, Zayna. Can you see my slides?
Yep,
Jen?
Everything looks great.
Very good, very good. Hi, everyone. Good morning, good afternoon. Thank you for joining us today. My name is John Damiano. I'm the CTO and a co-founder of Protochips. Before joining Protochips, I worked in the semiconductor industry in the 1990s as a device engineer. In that role, I was focused on process integration, how to use the existing and emerging process technologies to produce the next generation of microprocessors and memory devices. So today's webinar topic is near and dear to me, in situ electrical characterization. Today I'm going to discuss what it is, why it's important, how to be more successful, and then review some examples of experiments from our customers' publications. Hopefully you don't see that thing. There we go. At the end, we'll leave some time for questions. But before we discuss exactly what it is, let's talk about why characterization is important. Characterization of devices and materials is important because their performance dominates the performance of many things that we rely on every day. Everyone watching this is using a laptop, everyone has a smartphone, your calendar, your journal, practically everything is electronic. And practically all of our everyday activities are powered by electronics. And what you want from these devices never seems to change. You want them to work well, you want them to last a long time, and of course you want them to be cheaper and cheaper and cheaper. And the steps you have to take to achieve those things involve what's called scaling, as Zayna mentioned. And a good example of this is shown here. On the left, you see the first solid-state transistor that was made at Bell Labs in the 1940s. Fast forward to the 1950s and 60s, and the next big revolution there in the center was planar processing, where we could manufacture arrays of devices on a silicon wafer, not just individual components, but whole circuits. And this approach has worked for many years. And now you see on the right there a modern wafer here with lots and lots of circuits. So Moore's law describes an incredible pace of innovation, the number of transistors doubling every 2 years. And many people felt like that would have run out a long time ago. But scientists and engineers are creative people, introducing new manufacturing technology, new materials, and new device structures to push the limits of what's possible. And electrical characterization is at the root of all that. You need to be able to measure individual devices and components in order to scale to the next generation. For example, to introduce a new gate dielectric, to test new failure modes, to develop models so that circuit designers can do their important work. And like I said, scaling really is the driver of the whole electronics industry. Making devices smaller means you can improve their performance. Smaller means you can put more functionality on a chip. And smaller means that it's cheaper to manufacture because you can cram more die on a wafer. This is a photo of a semiconductor die here on the left, and then a cross-section of a memory array. Now, look at the jump from optical images down to electron microscopy as we push further and further into the device. And here on the right, you can see an incredible density of features. This is a multi-layer structure, a three-dimensional structure that uses numerous materials to implement a circuit. You have transistors there at the bottom, you've got capacitors, you've got thick and thin metals for power distribution. Everything here has to work for the whole chip to work. And the work part is where the electrical characterization come in. Does the new transistor structure drive enough current when it's on? Does it leak too much when it's off? Is this new contact structure that we've invented reliable? Or will it break under high currents? The only way to know is to actually measure it. So characterization is important, but why in situ electrical characterization? Why that next step? Well, it just so happens that a lot of the things that drive performance of individual devices actually happens at the nanoscale. Now look at this photo, and you're going to notice a few things. First, look at the scale bar in the bottom left there, 100 nanometers. So you're in the TEM. Second, even at this high mag, you have a huge array of devices here. You have incredibly small transistors. You have many different types of metal contacts. In the metal on the top there, labeled M1, you can see grains in the copper metallization. You can see this multi-layer FinFET gate structure on the transistors. So there's lots of different materials. Those materials have different morphology. You can see it's gone through planarization steps, thermal processes to deposit all these materials, and that defines the film stress. This is an extremely complex structure, okay? And it's not enough to just characterize these components individually. I need to know if this super via gate contact, which doesn't say, but it's probably a tungsten film deposited by sputtering or CVD with a specific shape and size. I need to know if that is 99.99% reliable, right? And I need to know what resistance to expect if I want to model and simulate this design. And more importantly, when something goes wrong, how do I get the understanding I need to fix it? In situ electrical characterization provides a path forward and maybe even a shortcut to answering those questions. So one key takeaway I think from this entire series of webinars will be the TEM isn't just for taking high resolution photos. Now, if that was all it did, it would still be useful because we really have no other way of seeing all these features. They're so small. Plus, you can measure lots of things that are of interest to device engineers, right? But adding in situ techniques allows you to do so much more, and it builds on your existing investment in TEM. Today's electron microscopes have a powerful set of materials characterization capabilities. By adding in situ, you can bias a device to its true operating conditions or even beyond. And then with this data on actual device structures, you can create accurate models, accelerate failure analysis, and correlate what you see to what you measure. So let's talk about how we provide these capabilities, what it takes to be successful, and review some examples of how researchers have used these techniques in the field. So first, let's talk about the fusion product versus what somebody might consider to be standard electrical characterization. So a typical electrical setup that you might find in a double E lab is shown here. These are the three main components besides the sample. You have some form of optics. You have to be able to see what you're probing. Then you have the probe station, right? So this part holds the sample, which is usually a wafer or a die, along with a set of fine electrical probes, and these are connected to micromanipulators. And these allow the user to land on specific contact pads on the wafer and make measurements. Now, usually there are 2 to 4 probes, sometimes more. Finally, there is a stimulus, a voltage or current source that can supply and measure electrical signals. Sometimes these are manual, you have to run them from the front panel, but often they're programmable to make a set of standard measurements and to plot the data. So if you have these things, you're ready to go, you're ready to characterize your sample. Now, the Fusion AX system has all these same components, but they look different. In this case, the optics is a TEM or STEM. The probe station is the fusion holder plus E-chips. Zayna mentioned this. I'll get into this in more detail. And the stimulus is the power supplies and software that are part of the fusion system. Now, let's look at all these three in detail. First, the TEM or STEM. So here, the optics are much more than a stereoscope that you might find on a normal probe station. And they offer unique advantages for in situ electrical characterization. Now, first, of course, you can take ultra high resolution images of your sample. Next, in addition to the optics and the camera, the tool usually includes a set of sophisticated analytical capabilities like EDS, EELS, or 4D STEM. And these give you way more insights into your sample beyond just images like composition, oxidation state, or electric fields. There's also it also provides you with a very controlled environment. It's like a giant Faraday cage that protects your sample and your measurement from outside noise. Now combined, this is a set of features that we can exploit to characterize these devices at the nanoscale and understand how materials and structure drive performance. Now, the electrical stimulus is provided by one or more power supplies with current resolution down to the picoamp scale. And this is important because by their nature, samples in the TEM are small and thin. And even really high current densities can still mean that you're measuring very low currents. Now with our product, we provide software control of the power supplies. You can program the sources and you can collect data. You can force current or voltage and measure current, voltage, or resistance. And better yet, all of those measurements that you make are synchronized to the images and other metadata through our Axon software, which makes analysis a lot easier. Now, the part of the system that I think is most different from standard characterization is the combination of holders and chips. The TEM holder and chips replaces the probe station for in situ studies. Probe stations are usually large benchtop units that don't have to worry about space, but to fit in the TEM, we have to miniaturize the whole thing to fit into a pole piece gap less than 2 millimeters thick. Now, most of you are probably familiar with a holder, like shown here. For fusion, we have connections to electrical cabling at the back of the holder. That's the part that sits outside the microscope. Those connections run down the holder to the tip, where, as shown here, we have 6 individual probes that will land on a chip. And we call these chips E-chips, as Zayna said. The 6 probes there can support different types of analysis or sometimes even multiple samples. Your sample goes on the E-chip. Finally, the holder, as Zayna mentioned, also has a tilt capability so that you can get your sample into specific orientations or angle it towards different detectors that the microscope has. Now, I mentioned the E-chips. As Zayna said, all fusion samples are mounted on E-chips. E-chips are a small silicon die. One side of the chip has contact pads, like here and here, and these serve as an interface with the probes on the holder. The other side has microelectrodes that terminate either on a membrane or near a notch in the die. Samples are placed on or near these microelectrodes, then they're attached physically and electrically, forming a circuit. The electrodes are isolated from the substrate by thin dielectric layers. So 2 examples of these styles are shown here. On the left, these are electrodes on a membrane, spaced microns apart. On the right, electrodes near a notch, again, microns apart. And which you want to choose depends on the type of sample that you want to analyze. Now, for chips with a nitride membrane, like shown here, these should be chosen for samples that are not self-supporting and need the nitride film underneath as a support. Examples of these types of samples would include thin deposited films that need to be deposited on a substrate, or small fragile samples like nanowires. These samples are imaged either through the 50 nanometer thick nitride film or through small holes that are patterned in the nitride. And we'll take a look at an example of that type of analysis in a moment. Larger samples, including fib lamella, have another option. We call these the fib optimized chips. Here the sample is mounted over a gap and connected to electrodes on either side of the gap. Once it's mounted, the sample can be thinned in place and then imaged and characterized in place. This design was created to solve a common problem with fib metallization, the deposition of metal around the sample. I'm going to talk more about that in a moment, but these are the 2 types of chips that we offer: chips with electrodes on membranes and chips that have electrodes beside a gap. And so, as an example of how they're used, consider a thin conductive film deposited over a finger electrode structure like this. So this gray is standing in for the sample. This is a material that's deposited onto that. You might form this with a shadow mask to confine its geometry, and we sell things like that as an accessory. After deposition, you can perform what's called a 4-point probe analysis. It's 4-point measurement. You can extract films parameters and electrical data and geometry. Extracting these parameters is important. They can be used to model the films for simulation, and they help determine how they're used as a small part of a larger process. For fabrication, you track them to ensure that this is a highly manufacturable process with a high yield. So the 4-point probe technique involves the sample spanning 4 leads as shown here. Current is forced through the outer pair of leads and therefore through the sample, the film, and voltage is measured on the inner pair. This approach improves accuracy because the added resistance of cabling, connectors, the electrodes on the chip, and the contact resistance can all be factored away, leaving only a very accurate measurement of the sample itself. Now, this is most important for conductive samples like metals or low resistance semiconductors, where the added resistance of the system is a substantial part of the total resistance. If the sample has many mega ohms of resistance, then this technique is less important. At that point, to be honest, good sample prep is probably the main issue. I'll talk about that in a second. But back to our thin film. So with a voltage and current measurement, we can calculate the resistance of the segment of material that's in the middle between the two inner electrodes. And if you know its geometry, which is easy to measure, its width, its length, and its thickness, then you can calculate its resistivity using the equation shown here. And this resistivity is a fundamental property of materials. It's not dependent on its geometry, but it could be dependent on the deposition technique you used to create that material. For example, sputtered materials or impure materials can have a resistivity that's very different than a bulk value that you might find in a book. And now that the geometry is easily characterized, now you can measure its width and length and the TEM and get a true accurate measurement for that material deposited using that technique. You can measure the thickness in a number of ways. Profilometer, there's ways to measure in a TEM. Going one step further, you can also calculate the sheet resistance in this way. So sheet resistance is really useful to circuit designers because it determines how long and wide conductors need to be, for example, to supply a certain amount of current. It also shows, for example, you can decrease sheet resistance by increasing thickness. You can see the trade-off here for a material that has a given resistivity. So for long runs of metal on a chip and some of the higher metal levels, you may need to go thicker to minimize resistance. Equations like this help you calculate what you need. So the sheet resistance feeds the models that circuit designers use. It also drives materials development. Like in some of the cross sections I showed earlier, used copper interconnect, right? So copper interconnect was introduced back in the 90s because aluminum was too resistive and was too prone to electromigration, right? So things like this help the industry move in the right direction in terms of its process technology. Now let's talk about accuracy. So I mentioned the first part, right, which is the use of a 4-point probe technique. This technique eliminates the impact of cabling, et cetera, and it allows you to get the most accurate results, especially for conductive samples. But there are other considerations that are equally or sometimes more important and that are impactful for all types of samples and all types of measurements. One of these is substrate leakage. Now, any form of leakage in your measurement is bad. You want all the current focused on your sample and only on your sample. Any current that flows around the sample and parallel to it and can't be accounted for will result in measurement error, especially for high resistance samples. And high resistance samples are typical in the TEM because, like I said, everything is thin and small, right? So one of the potential sources of leakage is through the chip substrate. The substrate is relatively thick, 300 microns, and the pads see the same bias as the sample because they're part of the circuit. Now, fortunately, this is something that the chip designer and supplier can address. All of our electrical chips are made with using a special substrate with 2 features: very thick silicon dioxide films under the silicon nitride top layer and a high resistivity silicon substrate. These layers don't add to the membrane thickness, right? So you can still do high resolution imaging, but they are found beneath the pads, the electrodes on the chip, and importantly, they prevent any significant leakage current flowing around the sample through the substrate. So with our system, single picoamp measurements are not only possible, but typical, right? These features also improve the AC characteristics of the chip during switching by reducing parasitics. Another, perhaps more important consideration is sample prep. Every sample requires some form of sample prep, and sometimes the prep itself can cause problems. For example, consider a fib lamella that needs to be electrically connected to an E-chip. Now, one advantage of fib is that in addition to cutting and thinning the sample, you can deposit metal onto it to form electrical connections. However, when you're trying to form several contacts within a small area, any stray metallization, like a thin halo of metal, can form electrical connections between the contacts and around the sample, right? So the key here is to avoid the overspray of metal that can lead to current paths around the sample and confuse your measurements. People have reported that tungsten is sometimes preferred to platinum because it has less overspray. You can actually change the metal deposition conditions completely to mitigate this somewhat. Sometimes you can make your fib cut larger, and this is now even more possible due to the rise of plasma fibs that are faster and cleaner. But one interesting solution comes down to chip design. As I mentioned earlier, we offer electrical E-chips without a membrane. So there's a physical gap between pairs of electrodes, and deposited metal can't span across that gap. The notch is long enough so that it extends beyond a halo completely. And this is a real advantage for FIB users since you can mount, form contacts, thin in place, and image at high resolution. Another solution lies with avoiding fib metal altogether. There's a group in Europe that recently published results suggesting you don't need fib metal at all. You can use van der Waals forces to form an electrical contact between the sample and the chip and mitigate leakage. And this is an interesting concept. So it assumes that the contact points on the sample align well with the contact points on the chip. So those are some of the considerations for accurate and reliable measurements. Now let's look at a few examples of electrical analysis from customer publications. I know we're going to have other webinars in this series that are going to highlight other work, so this is not comprehensive by any means, but hopefully it does inspire you to pursue in situ studies. Now on every slide, I'll provide a citation at the bottom, so if you're interested in more details, you can check it out, or you can go to Google Scholar, or you can actually come to our website. So I'm going to be quick. Let's start with an example that really addresses device scaling. Now, device scaling is, as we mentioned, is the process you go through to make a circuit on a wafer smaller. Remember the needs we discussed earlier. You want it faster, you want it cheaper, and you want it to last a long time. Now, scaling makes the circuit smaller, which should make it faster and cheaper, but it's difficult and it can impact reliability. And so we need to really characterize and understand the impact of scaling. Now, one concern is metal line reliability. Scaling means pushing more current through every smaller line on every single metal level. And you want to be able to push this as far as you can without impacting lifetime. And so how do you understand failures when they happen? Now, one of the problems you can see are fails at via levels. Vias are the places where the different metal levels connect. And they can be prone to the formation of voids due to electromigration and or stress. Now, electromigration is where the current is high enough that it actually pushes metal atoms in the direction of current flow. Now, as I mentioned years ago, the industry moved from aluminum to copper. This is important because copper is less resistive and less prone to electromigration, but every material has a breaking point, and often you're running these materials close to their breaking point. So understand what's happening under different conditions is the solution to overcome the problems, whether that's accomplished through new materials or new design rules. And situ techniques help you understand that. So here we have a fib lamella from a chip that's made with a dual damascene metal process, common in the industry. And we want to isolate a via from the circuit and image it while applying a bias. So the first step is to cut and mount the sample. Now, as we discussed earlier, our main focus is controlling the current path so that the current goes through the sample and only through the sample. So it goes through what we want to see, in this case, a particular via. Once the sample is thinned, you can see here on the left an array of many different vias and metal lines. But to control the current path, we need to, quote unquote, edit the circuit. And you can edit it by either creating cuts to break the current path in some areas or by depositing metal. And this allows you to focus the current on the target circuit element, in this case, a via that we want to study. Now, once the via structure is isolated, you can now start to do in situ imaging and analysis. So here on the left, you can see the voltage was slowly increased while monitoring the current and resistance of this via. Now, the breaks you see here, these vertical lines, these are times when the biasing was paused to allow closer inspection in the microscope. But what you see over time is that as voltage is increased, you do see a spike in resistance at a very specific voltage. Now, that's the type of data that you could obtain that ex situ perhaps with the right sample prep. But the benefit of in situ is now you can see why. What's the why? Why did that happen? So what the authors found was that the spike in resistance is correlated to the formation and growth of a void that's caused by electromigration. The authors also found that the location of this void depends on the polarity of the voltage. Positive bias on the bottom the electrode causes a void at the top, while a positive bias on top causes a void in the middle. So the benefit to the customer here is that identifying the physical cause, they can now target a more effective solution. Another example is the analysis of nanowire diodes using EBIC. Now, EBIC stands for electron beam induced current. When an electron beam strikes a material, it creates electron hole pairs, and these are collected. If they're collected, they can be measured as current. Electric fields that are present in the semiconductor can determine how well these are collected. And a scanning technique like SEM, or in this case STEM, can be used to map the current collected and therefore visualize the electric field in the semiconductor. That's a really powerful technique if you're trying to scale devices. The smaller probe size of STEM over SEM allows for better localization of these fields, albeit with a lower current. So here, the customer started by dispersing a set of these nanowire diodes across the surface of the electrical chip. Now, you don't want too many, or you could have them linking together to create a giant short, and you don't want too few. You want enough that you can choose from, and in this case, what you want to do is you're looking for one that overhangs the edge of a hole, like this, and with that, you can now deposit metal to connect either side of the diode to the pads on the chip. So the first thing you want to do is measure the diode and confirm that it has diode behavior. You can see here on the left the classic rectifying characteristic of a diode with a very low off-state leakage current. You can see here it's sub-picoamp at low voltages with a nice rise in current when it's positively biased. And by looking at the sample in the stem, you can also see that you've got good resolution on your images. The next step is characterization using EBIC. So here what the authors did is perform a line scan, so a 1D scan along the length of the nanowire diode. And there's lots of interesting data here. First, you see the shape of this curve on the left, this peak. The peak reveals the location of the diode junction. So when a beam sweeps across a semiconductor junction, the current goes up because the electric field that's present in the junction can sweep away those charge carriers and collect them as current. Next, there's data from the center of the nanowire versus the edge of the nanowire. So think of the wire as a cylinder. In the center, the stem beam is interacting with more volume. As you get close to the edge, it interacts with less volume, so it creates less current. You can also see less current with time. The authors measured it initially and then after an hour. After an hour, the current from both the center and edge goes down, so they can attribute that to the formation of a passivation layer, which would impact its characteristics. And you see a greater extent of that at the edge where the passivation layer would be more impactful. On the right, you can see SEM versus STEM data. Here, because of the finer probe size of the stem, though there's less current overall, you do a finer resolution that allows you to better localize the junction and make accurate measurements of current lifetime. Now, this can be extended to 2D by scanning across a sample. Here, different paper, the authors did EBIC on a fiblamella that has varying thickness from left to right, and the current intensity is plotted in the right in 2D. So the PN junction there is easily visualized in the current intensity, and it can be imaged as a function of bias. As expected, you see higher current from the thick regions. The authors also found that the electron beam energy impacts the spatial resolution that you can have at the junction. And so lots of different electronic parameters can be extracted from data like that. As a final example, let's look at phase change memories. So memory devices are a huge part of the semiconductor industry, and there's this eternal need for larger memories, higher density at lower cost, right? Among the different technologies that the industry has considered are phase change memories. Now, the one shown here is called GST, or germanium antimony telluride, which is the composition of that phase change material. So the advantage of this approach of phase change memories is that it's non-volatile, so it's like flash memory. It switches fast, it's scalable, and it offers the potential for multi-level cells, meaning not just 1 or 0, but multiple bits. The important thing, though, for Situ is that the microstructure of this material is what determines its performance. The resistance in the on and off state is determined by whether the phase change material is amorphous or crystalline. You have this 2 different styles here. On the left, you have this mushroom material style, or you have a structure that's encased in a metal liner. And testing suggests that these devices should offer a long lifetime. You can see here 2 e to the 12 cycles. However, what the researchers noted were there were some early fails in these GST phase change memories, and the question was why. And since this resistance depends on the microstructure, we want to understand what's going on. Now, the analysis here used a fusion system, but also an Agilent pulse generator, and these are the electrical conditions for set and reset. The electrical observation was that the set state resistance shifted higher. And looking at the device in situ reveals why. There's a void. You can see a void in this image. And using EDS shows that the antimony moves away from that bottom junction, leaving a void behind in its place. So the question the researchers had was, can you fix this? Well, the answer is yes. And they discovered a solution using in situ techniques. What they found is that you could heal it by forcing current through the cell. This heated up that metal liner around it. And after several positive pulses, the heat that was produced can forces the antimony back down towards the bottom, and the cell begins working normally. So this is an example of exploiting the TEM to understand an electrical fault, but then quickly developing a way to overcome the problem. And you can imagine the benefits to the user if you're trying to commercialize a new technology. So to wrap this up, what happens at the nanoscale drives performance at the macro scale. The in situ electrical characterization capabilities of the system leverages the unique capabilities of the STEM and complements the other types of characterization that you'll do. Success depends on a careful approach to sample prep. You want to be able to measure the sample and only the sample. I showed several examples of in situ electrical studies that were highlighted, and there's going to be more and more of these presented throughout the webinar series. And finally, just as the last thing, thank you for your time. I appreciate you tuning in today.
Hey, John, thank you so much for that. That was really, really great overview of truly from scaling and then to some examples of the technique being used. Thank you so much. Now we'll go ahead and do a question and answer section. So if you have questions and haven't put them in the questions box already, please do so, and we will relay them to Zayna and John. We do have a handful of questions at the moment. Zayna, I'm not sure if you're able to turn on your camera too, but if you are, we would love to see a face. But the first question I have here is, what is the optimal thickness of fib lamella when we prepare samples for EBIC or for in situ TEM studies? I don't know, John, if you have a recommendation.
I could give an example. The unfortunate answer is it depends. There are things about thin samples that are great, right? You can get the potential for higher resolution images. A lot of people thin their samples out because sometimes when you're preparing that lamella, you might damage the surface, right? And so that's an advantage. The downside, for example, if you're doing EBIC, is that a really thin section, it might give you better spatial resolution, but the current might be lower, right? So there is a trade-off there between resolution and current that you might see. Also, really thin samples, you could get stress while you're mounting it, right? So any stress on that can be more impactful. But that's the nature of preparing samples for TEM. So unfortunately, the answer is it depends. And part of that could be what you're trying to achieve. I will say it is really beautiful to see some of those images that I shared. I believe that was from David Cooper's group in Grenoble. To see that really high resolution EBIC was almost kind of staggering. And as somebody who's worked in the semiconductor industry, being able to visualize electric fields and junctions like that is a real breakthrough.
Yeah, that's great. And if you're looking for an EBIC system to, work with the Fusion AX system, Point Electronic has developed an adapter for our Fusion AX system as well, so that you can get their EBIC power supply and their EBIC characterization system that then combines with our Fusion system for results like those.
It's a great product. What they did is they made their system mount onto the back of the Fusion holder. The benefit to that is it pushes the amplifiers and all the electronics closer to the sample, which gives you better current resolution, lower noise, the ability to actually measure those fine signals. So it's a great approach.
Great, thank you. I guess next question would be like, when scaling and doing testing for the first time for an electrical experiment, is there a workflow that is recommended when applying your biases?
Yeah, that's a great question. First of all, as far as sample prep goes, we have a lot of, as Zayna mentioned, we've got a ton of information on our website about sample prep techniques and the things that you can do to ensure that you've got a good sample in the first place. That's key. The second thing, and I guess a problem that I've seen sometimes, is that you have all the stuff that you have to be careful with electrical characterization in general also applies to in situ measurements. If I sit down at a probe station to make a measurement, the first thing I'm going to do is put a grounding strap on my wrist. And that's because of electrostatic discharge. Your body moving around can actually generate lots of current, static discharge, things like that. And what you don't want to do is turn your sample into a fuse. And so even a small current on your body passed to the sample could cause problems. So what I encourage people to do, and what you can do through our software, is start small, set a current limit, set it low to start with, and once you're assured that your sample is doing well, only then do you increase what they call current compliance, right? So start low, go high. Don't start off with a really high voltage and real high current, because what you might learn is that your small thin sample is a really good fuse.
Thank you. What are the voltage and current specifications for the Fusion AX system? So I guess max and min voltages and currents. Zayna, that might be great.
I'll let Zayna handle that.
Yeah.
I'm actually, Jen, just for a visual, would you mind, am I able to share my screen?
Yes, let me set you up with that.
In your life, but
well, while Zayna's doing that, I will say that the voltage and current limits are good. They're important to consider, but note that those are limits, and often, especially for electrical characterization, you probably won't be working at those limits. Mainly because, like I said, you can achieve an extremely high current density, enough, for example, to cause electromigration of copper without a very large absolute current. So that is something to consider, the difference between limits and what you might prefer to use.
Okay, thank you. Zayna, here we go. You should be able to see it now to be able to share.
Yep. So I just wanted to provide a little visual guide as I talk, because I didn't include this in the original slides. I knew John would have talked a lot about some of the minute details of the different e-chips. But just so you know, our electrical for electrical characterization, we recommend a voltage of up to 55. While this is the recommended voltage on our specification sheets, if you have them, the sample holder as well as the e-chips can withstand higher voltages. This limitation is recommendation is simply relevant to your sample. So we always advise optimizing your experiments to see what your personal limits are. But again, our system can withstand higher voltages than that 55 volts. And then we offer two different systems for electrical characterization. You could either do, you can go down to nanoamp resolution or picoamp resolution. And again, it depends on the type of experiments that you want to run. And so they both go up to about 100 milliamps. And then with the standard version, which is nanoamp resolution, you can go down to 100 picoamps. But you have even better resolution with this high resolution electrical system that goes down to 2 picoamps. So it really depends on the customer, what they decide is best for their experiments, the type of sample, the type of experiments they want to run on the options that they have.
Great, thank you, madam. Another question here says, is it common to have the sample tilting during the experiment when using fib lamella?
I can take that one. Yes, if you have the ability to tilt, often, I mean, all holders can do alpha tilt. Fusion can do double tilt. The important thing there is sometimes you want to get your sample at what's called zone axis, right? You want to look down a certain column of atoms. The cool thing about fib is it does allow you to cut your sample in a way that you can cut along a zone axis, right? So you have a lot of flexibility for how you cut your sample, but then to get to exactly the right angle, you want the ability to use that double tilt feature. So yeah, it is absolutely common for people to use double tilt during electrical characterization.
Great. And then there's a couple more questions, but I'm just actually looking at the time and I noticed that we're a bit over. So what I'll do for those couple questions that are left, I'll just make sure that you're in touch with John and Zayna to get your questions answered. That's not a problem, but I do just want to be respectful of everybody's time presenting and those who are listening. So again, Zayna, John, thank you so much for your presentations today. Very informative. Again, everybody who is still listening, please go ahead and go to the chat and you can register for the rest of the webinars. We'll have some great presentations from researchers doing electronic device research. And again, thank you all for being here. I hope you have a great rest of your day, afternoon, or evening, depending where you are. Thank you,
Thanks, everyone.
everybody.
Bye, guys.